there's a lot of questions that come out of this for me. From my perspective, I want to understand, there's multiple ways I could go. I could say, hey, number one is, understand the hierarchy better. That would be one thing I could work on. The other thing we could work on is understanding motor better. Back to Vivian's questions, like, how do I move? How do I decide what to move? And for what purposes? Things like that, because these modules can move their sensors. They have the ability to control some movement. And why do they do that? Who directs that? And what kind of information would go back and forth to do that? And how would that motor information go from here to here? So that's another question, thing I have to work on to think about that. So, and then Marcus and I were talking about yesterday, I'll just throw it up here for grins. We were talking about how it is sometimes you can recognize a very specific set of features, and other times you can recognize something in a very sort of fuzzy set of features. Like the fuzzy set of features would be all coffee cups, but a specific coffee cup has a specific shape and specific size, or a face, like a particular face, like Lucas's. I recognize Lucas's face, it's a particular face, but then I recognize faces in general. And so we came up with this idea called the stretchy graph. The stretchy graph, which I could say like basically, how would you recognize things when you allow these edges to move a bit? It's like, yeah, the same features, but they're kind of stretched out a bit.
But you have to handle cases where you don't always have the same features. But Lucas has a beard and a mustache.
Yeah, I have to handle that too, right?
So it's not just stretchiness.
Yeah, I know. Yeah. The other thing related to this is states of objects and behaviors. So I would define a state of something is just the current position of all its features. And so if you want to think about stapler, the current position of all its features. The current poses relative to each other. Even something as messy as a t-shirt, you can say, well, I know the t-shirts have collars and shoulders and arms and certain features relative to each other, but that t-shirt could be on the table, it can be folded up. It's still a t-shirt. I still have a concept of it has those features, but I don't necessarily know where they all are relative to each other. And so when I pick up a t-shirt out of my drawer in the middle of the night, I will pick it up, I will find the collar based on the texture. And then I will run my finger along that, and then I can orient the collar relative to my body, and then I hang it up, and I know the rest of the things come down. So it's like all those features are there, but it's a lot of uncertainty as to where their poses at any point in time. So the knowledge of the links is really confusing at this point in time, but the local links always be preserved. I know that this part of the collar is going to be related to this part of the collar, and I can get there by moving along this way. So it's sort of like objects have the features that are near each other are more likely to have links, and you're stretching those links, but the remote features can be really off in distance. It's like if I think of an object, it's not like all the connections between all the features, but it's the poses between local features. Then you can stretch this graph and maintain the topology of an object, even though it's in a very deformed state. We have to be able to do that. And then sometimes those deformations have patterns to them, like the stapler opening and closing. So that would be like a behavior. Even if I look at your body, you're a set of features that you're like a t-shirt. You're a set of features that are in some, position relative to each other. But the state of your body depends on whether you're doing this or sitting down. It's like, I still recognize you. So again, it's this idea that the graph has like these components are all there. Your body parts are all there, but they're stretching out in different ways at any point in time. And somehow the model is able to deal with that. So that's another thing to look at states. So objects have states, your body has states, so all these graphs. Another thing is I just mentioned here, just remembered it. Another question is models in the where columns. That goes back to this point here. I could develop a graph in the where column. This would be the relative poses of your features relative. I have to think about it a little bit more. The question is there an equivalent model here, and what would it be useful for? If we think all cortical columns are the same, red columns and where columns, then you might have a model here and you say, well, how would I use that? One example is like when I drive my car, I get in my car, I don't have to figure out where the steering wheel is. Because when I'm in the car, the steering wheel is always in the same position to my body. And so I don't have to go out and say, infer the wheel, where is it? It's like, no, I have this model when I'm in the car, it's there, and I can reach it without even looking at it. And it doesn't really move very much from that position. So that would argue that I have some sort of model of the features in the car. When I'm sitting, I've learned that these are the features relative to that position, and I don't have to infer them. I don't have to rely on I don't have to say, oh, cars are composed of steering wheels and cabins. Where am I relative to the cabin of the car? I just know, I know where I am, and I might want to model that. So a lot of our behaviors might be built in this kind of model here, where you're saying, yeah, once I orient myself, I know exactly how to do things. So anyway, these are some topics here. And then finally, the Uber question is, when we understand this, even if we could build it, or even if we could build a more complex system, even if we could build a sub-complex system, when there's less than this, maybe we just build the first one I talked about, like you do just these modules and this learning system. Well, what would we do with it? That's a separate question. What would we want to do, demonstrate? What would we want to, what could we do with it that's useful? I didn't address that at all. I wasn't even thinking about it. I was just thinking about, hey, what are the mechanisms? How do we talk about this? So I feel this is, to me personally, this is real progress. I never had this clear conception of all these things before. This clear. It's much clearer than what's going on.
Yeah, it's a much clearer description.
Is it for you too?
Yeah.
Oh, good.
One issue you don't have out there, I think, is going to be important for any real implementation is this issue of what's a feature and how do you locate them. I think that's like the number one thing that tripped up standard computer vision. A lot of this stuff is, I could describe it in terms of kind of old style computer vision that they all ran and you can make decent demos and stuff with it, but to really get stuff working well, you have to deal with these fuzzy things of what's a feature, where's ambiguity, how do you deal with ambiguity, and it's not clear yet how that fits in.
That's a great question. I think we have enough information to start honing in on an answer on that. I'm going to, it has to do with this fuzziness of representation of space, right? In some sense. When I detect a feature, remember that the sensor says I'm trying to give a unique location to that feature, even though there might be substructure in that space. There might be some. If it was like, say, like an edge, I could say, oh yeah, I know the orientation of that edge. That's pretty easy. But even in that case, imagine you've got some sensor, and it's basically looking at some volume of space here, and it just says I'm getting some input, and I'm just trying to characterize it. I'm going to stick it through like a spatial pooler. I don't really try to understand what it is. I'm just getting some input, some bits, and I'm trying to classify it. Well, what if there was an edge, but at one point the edge is here, and the next point the edge is here, and the next point the edge is here. What am I reporting back? I think this is maybe the question you're getting at here. It's like, is this an edge, or is this an edge, or this one's out of the view? It shouldn't be. This one's more in the center. This one's barely touching it. So what do I report back from this? One way you can answer this is, in a sort of a binary way. You start off by saying, okay, is there anything in that space, anything physical that is in that space? This would be just saying there's a border. There's some edge of this thing, it's there, and I don't really care. I'm not going to make any further distinction about it. And you could start with that premise and start working away and say, how would this work under that condition? That would just allow you to define the morphology, essentially the boundaries of an object. It wouldn't provide any additional information. It would just say morphology. I'm thinking out loud. I'm just trying to think of how would you go about solving that problem. Think about it. I agree it's a big problem. I'll just put up here. I agree it's a big problem. Feature details. Feature. How would you find what would be a good word to represent this problem?
Subset.
No, subset's right. It's sort of,
It's almost like the granularity of a feature, and the
Yeah.
discrete feature,
discrete.
yeah.
You know, it's funny. Once you get to this upper level module, it's a hell of a lot easier because these guys are just all going to kind of result on some answer, right? It's sometimes it's easier once you get this guy because these are very, there's no fuzziness here. They're going to vote and pick something. You know, I mean, it's either faces or votes. It's going to be this or that. I may be wrong, but I'm going to tell you it's one thing. And so these would be very discrete properties. Where down here is where you start getting to the fuzziness. It's like saying, well, you know, I got some edge of an object and I'm trying to detect some feature. Where exactly is it? And is that the same feature? I mean, I think it gets weird down here. I think it's pretty clear up here. Because I've already bucketized it. I've already sort of put it into you know, into one of n buckets. Here, I guess what we want to do is we want the sensor to be to sort of do the same thing. It would want to discretize the feature in a way that doesn't cause problem. Maybe I can phrase it that way. So from that point of view, we'd say, okay, it wants to pick one thing or the other, and not let you have subtlety between them. Anyway, it's a good question. I don't know.
Yeah, if I would throw out a wild guess, I would probably say that in the beginning, features are just the raw sensory input. And then over time, you kind of learn to discretize it, to like group the sensory input into useful chunks of information. Like at birth, children can distinguish all different sounds from all languages. But over the first months of development, they lose this ability and they can only distinguish sounds from their own language. But can do this much more accurately.
That's a good point. You know, let me just rephrase that in a different way, Vivian. I'm going to rephrase it in my language here. If a feature is just some quality at some pose in the world, right? It's something that has a pose. And now I have a sensor that's trying, I should have drawn that in green to be consistent. Maybe, I don't know what. Let's see, green is a feature. And the black is a sensor. Well, and then I have a module that's processing that. The first thing I need to know is the pose of the feature. Generally, the location is easiest to determine in some sense. We can debate it, but in some sense it's easier. It's like, okay, where is that in the world? It's out here. I can, you know, it's at the tip of my finger. It's where my finger is, or you know, my eye. There's one column in my retina. There's this column in my column and a patch of skin on my retina that's looking in this direction, and I detect something at some distance. I might have some ambiguity about the distance, but it's pretty much, that's not like really weird. The weird part might be figuring out the orientation of the feature. And I've argued there are features which do not have orientation. So this is in some sense a color on top of that. You can say, okay, the most important thing is I detected something. And it may or may not have a pose. Some features actually don't have a pose, right? They just do not have, you can't distinguish, you know, I'm hearing a sound over there and the sound is a certain frequency. I can't necessarily say the orientation of the thing that was making that sound. Maybe I can, but generally I can't. So that's the system has to work with ambiguity on the orientation. And then there's this additional thing, these additional qualities, right? That are sensory specific. Things that only occur in vision or hearing or touch or something like that. So I guess what I'm pointing out here is that the system can start working with just location, and then we can start adding pose and these additional qualities if they're understandable, if I've learned them, or if you know, your example, the language, I mean, is like, well, maybe maybe I've settled, I've been exposed to these enough that I've settled down on a few of these that I can say, okay, those are the ones I care about. Maybe like imagine I'm taking these bits and I'm running through a spatial pooler, and the spatial tool is just trying to bucketize these things and saying, okay, that's it. That's what I'm going to know. And then I have to figure out the orientation of it, which is sometimes possible, sometimes not. It's a great general problem, but I think it's solvable. I don't see it as a.
Yeah, I think the way Vivian phrased it, to me, seems like you could go figure out some sort of a solution to a learning-based solution.
Yeah.
What she said.
Yeah,
Clustering-based solution, right?
Or clustering, yeah, or pooling or clustering or something like
Again,
that.
the thing that really gives me hope is that I don't actually need to know other than location to get started. The other things would be great if I could figure them out, but they're not absolutely essential. So there's a mix of orientation knowledge, there's a mix of quality knowledge that seem to be additional help. Those in the graph terminology, those additional qualities become some attributes of each node that can help, but are not really representing the graph in its edges. So a color is not part of the graph, and since it's a part of a node in the graph.
But a letter is.
What's that?
You have like a letter D, followed by letter O, followed by letter G.
Yeah,
You have dog.
yeah.
If you mix them together, if you don't know it's letter D, O,
Yeah, but
O, G,
those are in the graph.
those are
Right?
just 3 letters.
Those are in the graph. Those are like the D is in position to the O is position to the G, right?
But if you don't know what to feature in there, you just have a
Well, see, once I
letter.
get to D, it's easy. Once I've already detected a D, I'm already past the first level in the hierarchy here. And I've detected a D, it's easy. It's like D's are D's. There's no question about it. And I know where it is, and bingo. I think the problem we're dealing with is the first level of sensation, where you have a sensor reaching out to the world and it's detecting some, weird property that you're getting back, which might be in shadow or shade or this or that. There seems to be a whole bunch of extra things that the brain or the body does to try to help you figure out features, like how the retina compensates for changes in light, and how you're able to do divergence and whitening type of things. You know what I'm saying? There's a whole bunch of additional stuff that helps you figure out the quality of the feature, but the distance of the feature is the most important thing, where its position relative to the body is the most important thing. So again, when I get to the D, it's not a problem. It's like the real problem is I'm trying to recognize a D, and I'm doing it from just little patches that look for little edges or lines. And that D could be in black and white, it could be white and black, it could be written in script, it can be written all these different ways, right? And it can have noise, and so it could be 3D with a shadow effect. So I think the general problem of sensing a feature is you're looking at this thing and you're saying, well, if I'm looking at an edge of a, what is it? If I'm looking, when you actually just look at the raw bits coming in, it can be difficult to determine what's on that feature. I think the location can be known, but deciding what the actual orientation of the feature is and its qualities can be challenging. So I don't think the dog is a good example. Dog is like, yeah, I know it's a D and O and G. It's more like, how do I determine the D based on sensing little parts of the, here's another way of phrasing it. Go ahead. You got a D, and now I have a sensory patch that's looking at like this, or like this, or like this, or like this, or like this. There's almost a continuum of things here, right? That's the problem with this. So, I think, again, I get a lot of heartening knowing that what the ultimate goal is going to be trying to binarize this or quantize this, and so that's what we have to do. We have to somehow, I don't know the answer to it, but that's the problem. That's the difficult problem. Once you know it's a D, it's easy. It's like, we classify all these little weird things are Ds, and that's it. This gets back to the stretchy graph idea too, because Ds can have different shapes and different, it's somehow some relative set of features that are fuzzily, that are stretchy, morphology to them.
In terms of kind of demos and what we built, I think the obvious one to me is you learn an object in one pose relative to the body. You go to a different location and you can recognize that same object again. Like that's a hard thing for deep learning systems to do.
So that would involve just one model. Is that right? That just could be one model, or do you want to?
Well, if it's one model, you can just always output that category. You have to have at least a few categories.
Oh, no, when I say one model, meaning one modular system. That thing on the right represents many different models. It's.
So did you say one module or one model?
I should have been more clear. One module.
Module. Yeah, it could be one module.
Yes. Well, you could do like one module, or you could do all these multiple modules down here.
Right,
But I
right.
think you would start with the one module up there, which is
Just like our column stick, right? You do one thing and then you hook many of them and it's faster.
Yeah. So you could start with this. You could start. I don't know what's hard for a learning system to do. You could start with one sensor and one module, and that sensor moves around and build a model. Then you could extend it to multiple sensors in one module, but then that means you can only use one of these at a time, right? Because that's what's required to learn, that's what's required to infer, but you could still do that. Then you could go to, then you could add, then you could add the multiple modules here, and now you can do like the grasping with a finger, or, you know. I think, by the way, I thought it was an interesting.
I mean, for a demo, I think the multiple modules would be best because I'm just thinking vision again. You have an object, you learn very quickly what it is. You move to another location and you instantly.
Yeah, I can do that. I can do that with one module here and one module there, because this module can move. And I could.
Right, but then, yeah, it's just slower.
It's slower, but it's going to be, I mean, you could start there because it's slower, but don't forget, in a computer, we can do this really fast, right? I don't actually move. If I have a camera, I don't have to move the camera. I can just pretend like, I can just say there's this feature at this point over here, and I tend to this point, tend to this point, tend to this point, tend to this point. So this could be done with a single sensor that you can, at least, as long as you can, I can do it with a single camera, if you will. As long as the camera, I can subsample parts of the image of the camera. Then it'd be like different modules here.
Oh, then you have to move the camera.
But no, I don't have to move the camera. I could,
Oh, to have a different pose?
remember, imagine I have a camera. Here's my camera. And it's looking at an image out here that's like this, right? Imagine, so this is like an angled orientation, different orientations. I could check a feature here, and I could detect a feature here, and I can check a feature, here, by not moving the camera, but by taking this image and processing in a way that I focus on this.
It's like covert attention.
Yeah, and I focus on that. So it's interesting, if I had a camera doing this and I could do this really quickly, it would work. It also would work, even with a single camera, it would work if I moved it. And it should work even as I move it.
So that's why I'm thinking, after you move it, it should still work.
Yeah.
That would be impressive.
Or once you get it after you move it, you should be able to get it to work as you move it. You should be able to take a camera and say, move it around this object.
That's easier.
That's easier? Okay.
Yeah, that's much easier. Then it's just tracking.
No, but you want to.
I'm just thinking from an outsider's perspective.
Okay, I don't know that.
Right, if
To
you-
me, that's more impressive, but if it's easier, then fine.
Yeah, because that's a solved problem.
Okay, all right.
Once you lock in on something and you move around it and you keep saying, oh, it's still a dog, still a dog, still a dog. From the external point of view, that's easy.
Okay, and that's not what I'm mentioning. It's more like.
I know, but for a demo,
fine,
it would be
great,
hard.
great. I don't know.
I know what you're saying, but it's.
Because that's pretty damn hard, because you have to be updating all these locations as you're going. But I see your point, so let's put it aside. My point is, the simplest system you could start with would have this plus this in one of these, if I could move that. Second would be this plus this, plus multiple of these. Then I could say, I could look at this from these different positions all the time. Different sensors are helping out here. That, for example, imagine you had cameras, but this camera was obscured, but this one wasn't. Then you could use input from this
Are
one.
you thinking each module is a separate camera or a separate image path?
In that case, it would be a separate camera, a movable sensor. So that gives you I don't know again if this is impressive or not, but you're trying to recognize some object, and you say, oh, I recognize it, I learn it, and I recognize it. And now you said it's impressive. Oh, I see it from a different position. I recognize it.
Yeah.
Okay. My point is, what if I learned an object and now this guy was obscured and this guy was obscured, but these two cameras here at different positions are not obscured. So I can, even though I've never even, I could basically, I can say it doesn't matter, as long as I have some subset of these are able to look at this thing, I'll can figure out the object is.
But that's the same.
It's the same thing, yeah.
Well,
That's
it's,
like
I'm
the
not
same
talking obscuring, like I've now lost the,
What might be better is like no camera on its own has enough information to recognize it.
okay.
But together, all four of them.
I
have
don't
enough
know what's impressive. Here's the thing that's like weird, it's interesting to me is like, you're trying to recognize this thing and various senses are able or not able to participate at any point in time. And as long as you have a sufficient subset of them that are working, even if even if they weren't even used to train the object, they should work. If that's not impressive, fine, I don't care. I'm not trying to.
Yeah, because you could just imagine each camera has its own deep
Okay.
learning network and they get the exact same
Well,
inputs.
you can decide, I don't know. Well, they don't have the exact same inputs.
Well, I mean, they're trained on images. So if you can recognize a shifted object, you could apply that same system from a different angle. It's the same thing.
Okay. To me, it's much more interesting and impressive from a biological.
Because you know the internal.
Yeah. Okay, all right. Good enough. Anyway.
But the version of that would be interesting is if no camera on its own can sufficiently disambiguate the object, but then multiple ones can now recognize these things in novel poses.
Okay.
I think that would be pretty impressive.
Okay.
You do that with vision.
Huh? I'm thinking vision, but we
You know,
can translate to other.
what's really interesting about this, it could be anything. It could be, you should be able to do this ultrasound sensors. Anything that can detect some feature at some location, especially, I imagine a robotic hand, our hands can't really detect anything until they touch it, right? So I've always had this uncertainty about reaching into darkness because you don't want to hurt yourself. And if you have vision, then you say, oh, I see where I am. I see there's nothing in the way. But imagine if your fingers on your robotic hand had little, in addition to touch sensors, had little ultrasound sensors so they could detect how far away things are from each pad of your skin. This system would automatically be able to say, oh, I know what I'm about to touch before I touch it. I even know the orientation of it. So if I was going to reach down and grab something, it would be like I'm looking at it, but I'm doing it with sensors with my fingers. And they say, oh yeah, I know this thing. It is the orientation. I can now know how to grab it. So there's a lot of, we don't have to restrict ourselves to vision. You could build an object recognition system that works with other types of sensors that, like ultrasound or radar or even sound. The system should work in all situations, and it can be better in some than others. But so anyway, my point is we can think about vision, but don't want to be restrict ourselves to think about vision. And maybe that's what people will respect more. But to me, it's cool that you can do with any kind of sensor. It should work. Okay, so building this plus one of these as a starter, then multiple of these, and then adding these components would be additional steps on top of it.
Are you thinking there's a one-to-one correspondence between what and where modules, the way you've drawn it here?
Well, that's an interesting question. I've asked myself that. The way I've drawn it is that way. I don't know. It's interesting how the what columns and the where columns are separated in the cortex, not next to each other like I've shown here. And one obvious potential reason why that's the case is that the what columns have to communicate with each other very locally to communicate that way. And that information is directly shareable, where the information that goes between a what column and a where column has to go through a pose transformation, right? So that may be centralized. That could be another part of the brain saying, I'm going to here and then up to here. So this step here suggests that that it might be more fortuitous for useful for the brain to put these guys all together and then these guys all together, especially if there was similar voting going on in the where columns. So now you have a set of what columns instead of where columns. You can think of it this way. You say, okay, so here's my where columns. This is where. I have a set of what columns. This is how it looks in the brain. And these guys are voting. So there's a voting going on here. Maybe these guys are voting. We don't know yet. I'm guessing they would, but I don't know why yet. And then, but to go between these things, I might go down to this, to some point, it goes up to here. This is the kind of stuff that Marcus speculated, like, maybe it's a striatum, maybe it's a claustrum, something like that. Where there's these parts of the basal ganglia that look just like, they look just like this. They look like people speculated doing reference frame transforms. And now the question becomes, is there a one-to-one correspondence here? My first guess would be yes, but I don't know, it's certainly simplest to think about as a one-to-one correspondence. I can figure out what would work, I think, as a one-to-one correspondence. So maybe that's what we should do. But anyway, this could explain why the where columns and what columns are grouped together, including in the hierarchy, which we haven't talked about in the where column space. So anyway, the short answer to your question is we don't know. The long answer is I would assume there is a one-to-one correspondence until we know a reason why there isn't. Why would it be better not to have one correspondence?
Another thing is that I think envision the pose relative to the body is tricky to figure out.
The pose of the feature?
Yeah. In 3D.
Yeah, I think we should take this very abstract view of it and say, first of all, determine the location, then take these bits, run them through some sort of algorithm that does classification of some sort, like a spatial pooler or something else, to quantize them, the input, and then perhaps even at the first level here, the orientation is unknown. What if I just said I don't think that's true. Sometimes, we do know these orientation columns, but what if at the first level in the hierarchy, I just couldn't tell the orientation. All I can do is say, I'm going to quantize these inputs into different categories. I think the system would still work. Once I get up to here, the orientation is clearly known, but maybe not down here. So I don't know. I guess I don't want that to be a stumbling block. We can start with this, like, I'm taking these sensory bits, I got some location, and I can try to classify the input into discrete buckets and orientations, and we can leave that as a separate problem, like how do we do that? But I think the whole system should work even if I can't solve that right now. I'm not sure about that, but I think so.
Seems like this black line, formerly known as the bus, is. I'm trying to understand what
it's not a bus.
Right. Okay. Yeah, I'm trying to understand its role.
Well, we talked about
It's
this.
not okay. So it's not a bus.
We talked about this in the meeting we had yesterday afternoon. When we were talking about unit testing. There is no bus. It's a bad word. Shouldn't. These lines just show who is sending information to who under different conditions. And it does not imply mechanisms. It doesn't imply exactly how it's sending information. I'm routing information about poses and about objects. And in no more detail is specified here about how it knows where to go and how it's actually sent, or is there common communication structure, or is there a messaging system, or anything like that. It's more of a block diagram, and there is no bus. So that's why we get rid of the bus.
Yeah.
The reason why I had the word bus is I have this idea that you can take a module like this and just stick it in the system, and as long as it knows how to communicate with everybody else, it should work. In fact, yesterday Marcus brought up an interesting idea. He was wondering if you could have pre-learned modules up here, like face recognition modules, or modules not pre-learned, modules that are.
They come with some graphs already built in.
Yeah, they come with some graphs already built in, or a bias to certain types of graphs. So maybe evolution said, hey, for these face recognition areas, we're going to just sort of structure the graph already for you. And we're going to assume that there's, that it knows what faces look like generally. So not only are you doing a stretch in the graph, but you're pretty much going to assume everything's a face when I look at it. And it was an interesting idea. It's like, yeah, that's an interesting idea. Like, could you, so something, Marcus is thinking like, oh, you could build a face recognition system that has this built-in genetic bias to recognize faces because the graph is sort of pre-structured. And and plug that in. And they don't go through all the same data everyone else is looking at, but it says, I'm just going to try to think everything's a face. Distinguish between faces. And it seems like we have some innate ability to recognize faces and distinguish them pretty good.
Someone knows a Halle Berry neuron, right?
What's that?
There's a
Halle Berry neuron, yeah. I don't think that's built in.
So many different versions of that I've heard over
Yeah.
the years. It's
I
really
know.
funny.
Jennifer Aniston, Bill Clinton.
Yeah.
Yeah. I think they, yeah. So that's another interesting idea, like you could work on building, once you've got this infrastructure working, you could build modules up here that are more specific to different types of problems. So maybe, cortical columns are not identical, maybe some come with some genetically predisposed graph structure.
And the other thing that this would bring is if you have this prior that faces exist in the world, that in turn helps train your V1, expecting to sometimes see a face, expecting to sometimes see these two things called eyes and a nose and a mouth in a certain orientation, allows you to now train your V1. Your V1 has something to latch onto now.
Yeah.
There's potential there.
I would put that in this understanding hierarchy, because I didn't talk at all about, I said, oh, it is interesting how this stuff goes in this direction. But of course, we know that these things send things back down to layer 1 in this direction.
I was assuming they would just all be, you could treat them all as voting connections or.
I don't know if they're voting connections.
And what I mean, I'm sorry, the output of the models above also have green outputs.
Yeah, what, going up or going down?
Either.
Well,
So the
they're
output of,
different, I think.
the output of this guy, the green output,
Yeah.
could be fed to here. That'd be like It's like the expectations from above.
Yes, it could. That's if that would only make sense if these models and these models both had these modules and these modules both had a model of the same thing. So that was the example, like a large A and a small.
Yeah, but more generally, it could be a many to one or one to many,
Yeah,
just
it
like
could be, yeah.
between any two
Yeah.
modules.
There's a lot of variations on a theme here. I don't think I understand here. I was thinking specifically there's these, layer 6 connections that go back to layer 1 primarily in the lower regions. These are massive connections. And so these guys are telling this thing something. I don't know what that is yet.
But there's also skipping, right? We can have a sensor.
Yeah. So imagine, so that's an interesting idea. So what Lewis is pointing out is that this module here can get information from here. That's a direct layer. That'd be like a layer 3 to a layer 4 here. This becomes the input, the layer 4 input here. The output of this might be layer 3. That's a classic connection that Feldman and Vanessa would talk about. But there's also, if I have a sensor down here, that this guy seems also to get input from a set of sensors here. So a broader set. So it's basically getting sensory input from a bigger sensory patch. And so it could say, oh, I'm trying to detect some bucketized feature over this large area, or I can get this pre-processed green one. And one thing I thought was like, well, if there is a real consensus here, like there is an answer in green, like we know this is the letter B, then it may not, why would I even want to look at the sensory input? So there might be a precedent here, like, because these both go to the same layer. These both go to the input layer in here. They both go there. They have different places they terminate, but they both go there. So it's like, okay, they're both inputs. Well, one possibility is that if I have a green message that is, yes, we know this is the letter B, then I don't want to look at the lower level sensory details. I could, I suppose. But maybe I would just take precedence at. But if these guys don't know what it is, maybe it's like a big B. I wrote a really big B. And the low level V1 column only looks at little small pieces like this, and it's too much to build up a model. But this guy is looking at like big pieces like this. And he says, oh, I can learn what a B looks like in a big picture. So this guy can say, well, if these guys don't know anything, if this is a question mark, then I'll look at this. But if these guys do know something, then I'll just ignore that. It can be like that. That's one speculative idea. Seems reasonable because I can see how large things that are much bigger than the receptive volume of this feature detector, this sensor, would be very difficult to learn a model down here. It's just too big a space to occupy.
We also have a gating mechanism between those hierarchy.
What does it mean between this and this?
No, between the lower layer and the upper layer, like the thalamus.
Ah, thalamus, oh God. I didn't think about thalamus. Okay, well, I was hoping to avoid the thalamus.
Okay,
Uh,
that's all right.
We can avoid it, or I can speculate, which you don't know.
Should avoid it.
Okay.
I think it's,
I do have a question. We've been talking a lot about object detection, localization, and not about prediction. Is that gonna come in later at some point? Does that
Well,
come
you
back?
have a model, right? And with a model, you can make predictions.
Right.
So we have the data to make as many predictions as we want. I guess the question is, under what conditions should we be making predictions? So locally here, let's see, if I know what model, what object I'm viewing. So let's say my green is determined, and we say, oh, we're all looking at the letter B, and then I somehow know I can take that. I know the location of my sensor relative to the B. I should be able to run this model backwards and predict what my sensor should see. So fuzzy, the information is there locally. As my sensor moves, I should be able to predict what feature I'm going to see. So it'd be a local thing here. Clearly, if you violate your prediction, that's useful for attentional mechanisms, which we didn't talk about at all. There is the infrastructure here for making predictions. So we need to find out why we want to make predictions. And
one example of this, like, if you look at this situation, the table is covering the chair. So I can't see everything in the chair, but because I have a model of the chair, I know I can predict the way the chair is. If I know I left my cell phone on there,
yeah,
I know how to reach in there and grab it, right, without ever having
you can
viewed it.
even
It's-
imagine the chair. I can visualize
Yeah,
what the
we
chair
can
looks like.
imagine,
On
yeah.
there. It's like I can picture it. It's like
Yeah, so being able to understand the structure of things you cannot directly sense is
Yeah.
pretty powerful. That's a type of prediction.
yeah. So I think what might happen here is we start building some subset of these things, and that we can test and build, and it's a joint exercise to figure what that is. I won't say I know what that is. As we do that, we'll think of ways of doing clever testing on it. We'll think of problems that we haven't solved that we want to solve. It will start being a scaffold in which we can build more and more details on. And that's what was exciting to me about this whole idea. Is I see this as a scaffolding in which you can start building the whole damn thing piece by piece, figuring it out as you go. Where before I had no idea.
Is the output of a wear module is
Yeah,
the pose of the feature relative to the body?
No.
This-
Well, that's
this-
one.
this-
Yes,
this thing.
yes, that's the
Yeah.
feature relative to the body. That's it. That's just, yeah, you're right. It only does that, by the way, if the green answer isn't known. Like, for example, if I see there's a letter B, I want to send down to this module down here. Oh, I'm seeing an edge at this location, right? It's sort of the same sort of priority. If I know there's a B, I want to send the B down to here because this becomes like the input, just like this became the input to that module. It's like, oh, then I want to build a model of the B's relative to each other, relative to A and the C. But if I can't recognize it's a B, then I'll send down the low-level features and I'll learn what a B is. So you don't always. This guy locally has to determine the feature relative to the body. It has to do that for any of this to work. It only sends it down here if for some reason I need to attend to that feature, either because I just decided I want to attend to it or because I don't recognize the object yet. Like if I can't recognize the object yet, I just have to look at features and say,
Why can't it be always sending it and that guy decides what to listen to?
well, because sometimes it has to look, well, it could. Okay, it depends on how you want to consider the messaging here. So it's the same question we have here. It's the same question we have right here, right? You can say, well, I can give you the details or I can give you the big picture. If I know it's a B, I don't want to look at the details. Why would I want to remember that? now I'm trying to build a model of the letter words. So yeah, you could send it here. I'm just, yeah, you could. Again, don't think of
It's
these.
just sort of information being available.
But
and that
yeah,
kind of
but
thing.
I wouldn't always want it. If my goal here
Right,
is,
right.
I want to recognize the highest level object I can. I want to build the biggest, highest level graph that I can. And so when I look around and build a graph of this table, okay, Marcus today is over there, Lewis is over here, and today I have my coffee cup and I bought my own pens and there's my laptop. Okay, I got all that to my head. I just built this model really quickly here. I don't really care, like, what was the exact orientation of the pen and what was the, or what was the, the edge of the pen relative to the cap of the pen? Like, I don't care. These guys are looking at that, but this guy, I don't really need to know that. If I completely didn't understand the scene at all, I have no idea what it was, I would just be looking at little features of what's going on here. So I guess in general, you want to prioritize for higher level green objects, features. This is just a normal type of feature. You want to prioritize that down here, just because that assumes I've already learned the components down here. So as soon as I learn the components down here, there's no point in relearning over here. But I could if I wanted to attend to it. Right? If I said, today I really care about exactly where that pen is. When we look at it carefully. Oh yeah, okay, the cap's this way, not that way. But the camera wouldn't notice that.
If we only have one module, let's say this thing and this, we don't need this, right?
No, you don't
We
need
just
that.
have this.
Yeah, that's
okay.
it. Yeah. And you could start with that, and you could add this and this and
But
that.
then you need those little ones.
No, you don't need little ones because this allows you to build your model with different sensors. I'm not sure if you think that's interesting. That's like saying, oh, I could learn this object with my finger or another finger or with my eyes, but
It's still one object.
it's still one module here learning. But to me, it was interesting the fact that I could touch the pen with any part of my sensory scan and it would work. It just doesn't matter. I thought that was interesting from a machine learning point of view. Maybe it's not interesting at all. I don't know. It's really interesting from a brain point of view. It's pretty impressive. You've got tens of thousands of these things, and any one will work. It's like, oh, that's pretty cool. But you don't need to do that. You can just pick one and build this model. This module, have a module with one sensor. Then the other beauty about it is whatever you use to design this combined module here, pretty much work down here too. It's pretty much the same thing.
That's what I'm thinking, yeah.
Right? There's no advantage of having this here until I have multiple of these guys.
Right.
So maybe that's the way to think about it. You've got a simple, you argue this is really too simple. Well, it is kind of simple. A sensor, maybe the part of sensing a feature is not so simple. But if I have feature and orientation, translate it into body location, easy. Then I have to build these two things. And I argue we know enough to get started on this. I'm looking at Marco. I think so. You think so?
I'm still I don't know.
All right.
I'm still figuring out what's going on.
Okay, I'm sorry. All right. We've talked about how to build these graphs. This is like what we did in the college paper. This is
Sure,
what we
yeah,
did with
those work.
graphs. We can make a module that does this. We can make a module that does this here. We can easily do the reference range transformation between them. This models will not have everything we want. Maybe it doesn't have stretchy graphs. Maybe it doesn't do this, it doesn't do that, but it can work. And we can build that and rebuild that. Over time, we can improve this, but we could, whatever, you could almost take this like this code base that you did to do this, you plug in right down here with a different learning rate. And then you could go bing, 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 bing. Or it could be fast learning down here. It just means that you could make these, there's an interesting variation. In the brain, these should be very slow learning.
Oh, yeah, you could do it.
Be very slow learning because these guys are going to rely on the fact that these green arrows aren't.
That's the advantage. Even with one module, that's the advantage of that guy. Is
And
that it will be slow,
you've got the green.
and the one on top is for sort of really fast one-shot learning. and
Yeah,
things like that.
yeah.
But
But I could make these fast too, as long as I didn't have a hierarchy. Then I would be able to.
How to stabilize on the green.
It doesn't matter because I'm not using it. All I'm using it for voting. Anyway, these are variations on a theme. I don't think it really matters. Here's like I do the one-shot learning. Like I go to look at the table. And I love the example of the food on the table. And you're looking at the potatoes, there's the green beans, isn't it? You're building this one-shot like module here. At that point, if I wanted to recognize it again, I'd have to go, like, I walk in the room from a different direction. I'd still have to look, oh, there's the green beans, there's potatoes from a different orientation. And I wouldn't be able to do this one-shot recognition of everything. But I could if I had these guys going really rapid. It's an obscure point. There's dials you can turn here and make these things do different things. But defining this as one module, we've identified two big problems. One is how do you discretize features? That's one problem, the big problem. The reference frame calculations are easy. The other problem is, well, let's be precise about how these graphs work and how these things work. I think we know enough to do that. I feel I know enough to do that. We'll find out, but that would be another big project. Okay, we're going to given a feature at some location in space, convert it into a location of the object. There has to be a quantity, which is the pose divided to the object, and now we build this graph with the idea that we're going to be able to infer which of these graphs, which object we're viewing based on a series of observations. Well, I think we can do that. I think I could identify the steps that have to occur. I don't know how I code it. I don't know how I do it, but I can identify the steps that happen.
I would just start with something like a column splitting, column sweeper,
No,
not
that's
voting,
not-
but within a column.
Yeah, well, that would be like the columns paper is like this part here. With temporal pooling, so we have a stable representation of it. So these guys get temporal pooled here. But where these are not just features, they're poses of features. Right, that's the difference. In the columns paper, we just said there's a feature at some location, which is like no pose. All right, it would work.
And no,
But what,
and no reference.
Yeah, I would almost do their edges of the graph.
Yeah, yeah.
well, we
They're
didn't,
relative positions of two features.
well, in the columns paper, we didn't have that. The
No,
columns-
I know.
Yeah,
but
I think
but that's
this.
what an object is.
Yeah,
It's
but
a
I
bunch
think
of
the
things
object,
that
I think the object might actually, this model in here, a model in here, might actually have both. I'm not sure yet. They might have both. You might have what we did in the columns paper, which is remembering features that pose, feature that pose, feature that pose. You can also, in addition to that, you can build the graph. And I think there's some advantages to doing both. And we
Yeah,
might have
because if
both.
you have a very unique feature, you don't need the graph.
All right. And
So what's the
also,
difference than that in the columns paper then?
Well, same thing. In the columns paper, we had that too. We had a very unique feature you could recognize right away.
I think the difference is the edge, is the reference.
Yeah, but the algorithm could be the same. It's just what are you pulling?
by the way, if I imagine, this is the way we did like layer 4. Remember layer 4 was some like, it's like your feature at some location. Well, let's say it was this feature at some pose relative to the object. So we just extended it a little bit. You could dynamically build up this graph as needed with this data. Like I wouldn't have to store this up front. I could, but I could also dynamically.
Right.
So here's an interesting.
Which is advantageous.
Yeah. Here's in some sense, this is an efficient storage mechanism. This is somewhat inefficient. This is an n squared tech problem. It wouldn't be, but it potentially n squared problem. This is just a linear list of features that poses. I think you could calculate given any two of these things, you could calculate an edge up here.
Right.
And therefore, all the knowledge you need is contained here. So it brings up the idea that you might, I don't know, I'm thinking, but you might be able to dynamically do the equivalent of the graph with this information. I have to think about that.
No, you can. You can.
You're
I mean, code you can.
Yeah.
I mean, there's a neural system.
Yeah. Also, remember, we can run things much faster than neurons again. So, what might take, hundreds of milliseconds or tens of milliseconds in the brain, the brain doesn't want to do that. We might be able to do it super fast and just run through all these combinations really fast and just, bingo. I don't know. It's an interesting question. Here's just imagine just diving into details. What am I getting here? I'm getting, all right, I don't want to start just thinking out loud.
Yeah, and I actually have to leave soon
Okay.
for my
Okay.
talk/doctors.
Okay. So that's it for today.
I think as an outlook for a cool demo on a big, larger scale, I would say that any behavioral task would be easier to solve with this as a backbone to understand and conceptualize the world as opposed to using high-dimensional sensory input. So it would be cool on a next future step to test this on like a behavioral task or something.
When you say a behavioral task, what do you mean? Give me an example.
Just anything you need to do in the world, like Subutai had the example of picking up the phone from the chair. Would be so much easier if you have all these models to understand the world as opposed to having the raw sensory input from your retina, basically.
I agree. So here's my problem with it. That's my number 2 up there, right? Number 2 is motor, right? Work on motor stuff. My problem is, you seem like you're right. All the information we need to solve really interesting motor problems is sort of here in the system. But I don't know enough about what people have done in this space. I don't even know enough about what they've done in the neuroscience literature. I don't know anything about what they've done in the robotics world. So to me, that's like a big open, like, oh crap, there's a lot of stuff to learn there. For me personally, maybe for you could figure out, I don't know. So to me, like, yeah, I want to work on that. But it's a bigger, it seems to me like a somewhat daunting problem because I don't even understand how to phrase problems. I don't even know what a very specific task or problem that I'd want to solve would be. If we could articulate some very precisely that things we know the brain could do that people don't know how it does it, then that would help me at least think about it. Maybe other people too. So I agree with you. It's just like, oh, it's an unknown space for me. It's
Motor commands, I mean, in general.
what's that? Just how even just asking what is a difficult motor task for a robot hand to do? I mean, I don't even know that. What is like, sometimes I'll say something and supervisor will go, oh, that's easy. Like, everyone knows how to do it. Okay. And other times I'll like, this is easy. And he says, oh, that's really important. Like, I don't know. What are the equivalent, touch points in robotics?
Yeah. I would definitely say there's a lot of room for improvement in the field. And I think that having such a model in the background would make it crucially more efficient because it adds so many inductive biases that are specifically for the kind of 3D physical world that we live in, that it would make it a lot more efficient to learn and understand.
But I need some specific problems that people say this is hard to solve. And they need to be, anyway, that's what I need. Like, I don't know what those are. Just be honest, I just don't know what they're.
Christian.
Oh, Christian. Sorry.
Maybe,
Sorry.
Sorry, Chris. I just didn't make the connection between Chris and Christian.
so can we at least like start talking about that? And I'd propose again, maybe you know better than anyone here, what are like the difficult challenges in the field. Maybe you can propose something, like give a short presentation and just so we can get the ball rolling on that as well.
Yeah, sure. I can make a short presentation on like some of the challenges in the field currently.
Yeah. That'd be helpful. Another thing that scares me a bit about it is anytime people start dealing with your physical movement, and then you either you have to have a physical robot or you have a simulation, and people always say that simulations really don't capture the problem. So you surely don't want to, I don't really want to delve into building physical robots here. So there's that aspect too. It's like, how do you, what makes a sufficient demonstration that you can do something? Is the simulation good enough or not? And it's a lot of work to do simulations. So that's another, just think about that a bit. gonna want to start a project that takes us a year just to get the physical mechanism working.
But well, luckily these days, the simulation's a lot easier than it was in 5 minutes. We have tools at our disposal. Physical robots are still very hard. I don't think we have to go there, but simulations are quite.
But
Depends how realistic you want to be.
well, I've heard in sort of the general experience that simulations are sort of discounted because they don't really deal with them. They don't really deal with real problems. So I don't know if that's true.
That it used to be more true in the past, I think, but the recent, the recent environments, sorry, I got the print.
I'm sorry.
Sorry.
Take your time. Recently,
Seems like virtual reality might be an area to build,
oh boy.
Well, there are
if you don't want to build
simulations,
it in real.
there are simulation environments that try to be realistic for testing robots, but I don't think that's what we want to go, because those are slow.
I don't know.
No, they're not so. That's my point. Like,
Yeah,
for example, the ones we're discussing, iGips and Hapta, they are very realistic. They're getting from realistic things, and they're fast. So maybe 5 years ago they were slow.
I was
not
looking
the
for a
big
2021 paper, they were comparing them, they're about like 4 times real time.
What's slow in doing
No,
what?
Habitat's like super
What do you mean
fast.
slow?
I disagree. on
What,
that.
what does it mean slow? Doing what is slow?
Well, we have to run multiple experiments, right?
Maybe.
That's the question. If you're just trying to simulate in real time, yes, but if you try to run multiple experiments,
You say real time is too slow. to do
Correct.
that. And if you're trying to do machine learning,
Yes.
typical machine learning.
that's my point.
You need 1 million samples, but we shouldn't, the whole point of this shouldn't need that.
That was my thinking. Like, we're not doing
Yeah.
this should be fast. This should be super fast.
Yeah, exactly. That should be the advantage of having this model, that we can dramatically increase the sample efficiency.
I mean, this really should do one-shot learning in the sense that one-shot meaning since one feature at a time is sufficient. Like I can't learn a new composition or new object in one presentation, but I can do it by doing a series of presentations, one at each location, and then I can build a model. So it's close to one shot, but you shouldn't have to do many presentations unless you're trying to learn one of these lower ones down here. Those which are learning statistical regularities in the world, you have to do multiple training sessions. But this up here, this module will be quick. Well, I don't know, those are interesting implementation details. It would be great if you could present, as Lucas suggested, some sort of like, these are some of the key problems that people would really think was amazing if you could solve.
Yeah, sure, I can do that.
Just to chime in here, I think we would want something that's a lot faster than real time to train these models.
Yeah, but like this, for example, the habitat we're discussing, it's running at 1,000 frames right per second, something like that. That's crazy fast.
Yeah, exactly. That's what I'm saying. It can't just be. It has to be much faster than real time.
Yeah, no, but machine learning is still super hard on those, but as long as we're not doing machine learning, it's still.
So if I were to prioritize these, I would say, look, we can build a system like we talked earlier about that recognizes something from different positions. And if that's an impressive thing, we should do that. The motor part, behavioral part is going to be harder. And it's going to take a lot more discovery. And we don't know how to do that yet. It may become obvious shortly. That's my hope, because now I have a framework to think about it. But it is an unknown. And so there's a lot of unknowns in it. So I wouldn't pick that as the only one to do. I think we can start working on it, but I wouldn't wait till we figure that out. I don't know how long it would take to figure out those components.
Yeah, I mean, I wouldn't say start on this tomorrow, but I think this is where we could show the most impressive results in the long run, because in the end, our brain, that's what it's trying to solve, trying to behave
I agree with
in this world.
Yeah, I agree. I mean, in a sense, you know, AI and robotics are going to merge into one in some sense. It's all the same mechanism. So we should be able to solve really interesting robotic problems with this. All right, well, you can make a presentation on what would be an interesting problem.